Let's go for it, yeah? Okay, we've been given the green light. Hello, everybody. Hello, hello. Is everybody comfortable, yeah? I would love you all to be comfortable to enjoy this experience. Before we begin, let's do a little hand-raising exercise because I love those sort of things. Raise your hands if you use Git on a daily basis. Oh, thank God. Okay. Okay, second. Raise your hands if you use Git using Git commands in the terminal, in the command line, like a real boss. Oh, yes, yes. Okay, I think you'll like this then. This should be fine. And last one. Raise your hands if you've ever had the courage to look inside of the .git folder. Okay, that's a good ratio of hands. All right, by the end of this session, you all will have done, hopefully, if I do my job right. Right, let's get into it. First of all, thank you very much for coming to a Git-based talk at an Android Dev Conference. I very much appreciate that. Ladies and gentlemen, welcome to Basecamp Git. Located somewhere inside a project folder, I will be your guide, your illustrious warden through the dark caverns and chasms of the .git cave. I will keep an eye on your physical well-being as well as your mental sanity. My name is Ben Cadell, and I'm a senior Android developer at a company called Babel in Berlin. The sponsor booth is downstairs. When I'm not Androiding, I love Bash, the terminal, and for some reason got really obsessed with Git, which is nice. Selfish plug, I have a YouTube channel. So if you enjoy this ridiculous nonsense that you're about to see, then maybe check out some of my other garbage. But what is our mission today? We have 3 objectives. 1, to safely cave dive into the .git cave folder. Secondly, to map it and explore it, and through exploring it, understand a little bit more about how Git works internally. And most importantly, finally, we will all together safely return back to the surface with no one left behind. Oh yeah, somebody knows what's coming. But before we go, we need a little safety briefing, a little pre-mission checklist, if you like. We need some items that we all have together in common before we go into this dangerous cave system. 1, we need bravery. And before coming to this talk, you all signed the mandatory health and safety waiver, saying that if something happens to you that you can't sue. That's very brave of you. So well done. Next, we need basic Git experience, and this is not an introduction to Git talk at all by any means, so let's just remind ourselves what Git is in case we've forgotten and turned up to this Git talk. Git is a version control system, meaning that it tracks changes to files and folders over time, blah, 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 blah. It's the most popular one. Arguably, you can use it through a GUI like a loser, or in the command line like a winner. It is powerful, deep, and complicated. In the bottom right, you'll see some Git commands you might notice, git status, git add, etc. And in the top, you'll see this sort of commit diagram that you'll see all throughout the world of Git. Each nodule, each circle represents a commit. A commit is a snapshot in time, a save of the project in that very moment. And obviously, as your project changes, one commit moves to the next, and so on and so forth. Git. Git 101. Done. Of course, before we go into a dangerous cave system, we need some safety equipment, some tools. So let's just make sure our packs are complete. 1, we need a map. And unfortunately, our maps are not complete. The cave system has not been fully explored. But in future expeditions, we will attempt to complete the map. But for now, our map is our terminal. Secondly, we need torches, flashlights, to illuminate the darkness of the chasms and see the files and folders that exist in our cave system. Yeah, it's getting strenuous at this point. That's our ls command. Third, we need some rope to safely traverse between the caverns of this cave system. That's our cd command. And obviously, importantly, we need rope to escape back out the cave, climb back out at the end. And obviously, we need helmets to protect our heads from rocks and stuff. Yes. Anyway, that was your stuff. We have our tools, but you all must be tired. It's getting late. You have a big day ahead of you tomorrow, so go back to your tents, get some rest, and I'll see you in the morning. Spinning around to denote passage of time. Good morning, everybody. Yeah, I'm sorry, it's a lot of this. It's a lot of this. Good morning, everybody. Grab your things and follow me to the precipice of our adventure. This is the entrance to the .git folder. The .git cave. Lean over the edge, but be careful, don't fall in. It's a deep, dark chasm. Every project that uses Git has one of these hidden .git folders within it. It's how it makes the whole Git system work. It's hidden because in the Unix world, a dot in front of a file or folder simply means that it's obscured to the generic ls command. You need to use -a for all to see all the things, including the hidden ones. Now, ropes on, belay on, other climbing words, helmets on, and let's CD into the .git cave. Oh, this is me rappelling downwards. I hope that makes sense. As we begin our descent, we turn on our torches to illuminate the rocks around us, and we can see below us some files and folders slowly start to appear out of the shadows beneath us. And everything is fine until our rope, the thing that holds our very lives in its hands, begins to wane and fray, and eventually snap, sending us plummeting into the darkness below. Oh God! Nobody panic! I've got a flare! Oh my God! I'm getting too old for this crap. Oh, it's quite the fall. Oh, is everybody all right? Are you okay? You're not hurt? You're all right? You look a bit hurt. No, you're okay. Oh, thank goodness. Our rope! It's destroyed. We're not coming back. We're not going back out the way we came in. It snapped. Oh, imagination. Okay. All right, everybody, don't panic. There has to be another way out of this cave system. There just has to be. We just need to find it. Let's get our bearings together, okay? We are here in the .git folder. Our way out is not the way that we came in. We have some folders and we have some files. I think our best course of action is to systematically go to each file and then to each folder, understand it fully, and see if we can find an escape route at each one. Yeah, let's do that. Okay. Before we go into this ridiculous adventure that will probably take the lives of a few of you, we need to know a couple of things. These things that you'll see all throughout this cave system are called hashes. You'll see them everywhere. Git has these hashes everywhere. Commits, for example. Commits, which hopefully you're all familiar with, each have their own unique ID, which is one of these hashes. They are a SHA-1 hash, and they are created by the contents of the commit, which is cool. So we can refer to each commit by this ID, but luckily we don't have to tell Git all 40 characters when we're saying, hey Git, look at this commit. You can just give it 7 characters, or enough characters for it to be unique. Nice, so there's hashes, and they're everywhere. Next, very important to know, in Git, there's not just commits, there's other type of objects that exist in Git. We know we have commits. Commits have their own unique ID, which is a hash. But did you know that a commit, inside a commit, in the metadata of the commit, if you like, it points to another type of object called a tree object. A tree object has its own unique hash as well, and a tree object can be sort of thought of as a blueprint, a printout of the folder. So, in this tree there's this file, this file, this file, this other folder, this other tree, this file, this tree, this folder, this tree, blah, 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 right? A tree object. Nice. So commits point to an individual tree that have their own unique hash. And trees, if you hadn't already guessed it and filled in the blanks, trees point to something else, the final object in our Git world, a blob object. And a blob object can be thought of as literally the contents of the files. So where a tree says, there's file 1 here, the blob of file 1 would say, hello world, or I'm file 1, or whatever's inside of file 1, right? So commits point to a tree, and trees point to blobs, other blobs, lots of blobs, and other trees as well. 3 type of objects. Keep that in your noggin. Okay, ladies and gentlemen, I don't want to panic you, but our supplies are very, very limited, and we don't have the resources, the water or food, to survive long, so we have to go fast, okay? We'll start with the files, we'll go through each of those, keep your eyes open for anything that might get us out of this hellscape, a loose rock, a beam of light, a nice breeze, anything that will help us escape. Keep up, let's go fast. First file, commit edit message. This is horrendously boring and contains the last commit message used in the repository. Easy peasy. It also contains the commit message if you passed it in line with the -m flag. If you did git commit -m message, it will contain it in this file. That's what the file looks like. It's a commit message. Boring. Let's keep moving. No exit here. The fetch head file. This one's a little bit more interesting. It updates automatically every time that git fetch is used. Now, remember, git fetch also happens as part of a git pull. because a git pull is just git fetch followed by an immediate git merge. So fetch happens a bunch of times. And what does this file fetch_head contain? Well, it contains hashes of the named references that exist on the remote. What the hell does that mean? It's basically a list of branches and tags that are on the server. Easy peasy. Let's look at the file. Let's break down some of these columns to understand them. First, the first column is a SHA-1 commit hash, like what we were talking about before. This is a unique identifier for a specific commit in our history. Cool, okay. The next column, saying not for merge, is a little bit of an interesting one. Remember, if you use git fetch and you're being very unspecific, git fetch will download all of the remote tracking branch information from the server, and you don't want all of those remote tracking branches to be merged into your local branches. That would be utter chaos, right? So this line here tells git, no, download it but don't merge it, don't merge it, don't merge it, right? Unless you're doing a git pull where you do want to do a fetch and a merge, and in which case this bit will be blank. Next column is the type of thing. The type is a branch or a tag, the name of the thing, and, the remote URL that it's coming from. Easy peasy, fetch head. Nice, let's keep moving. Next, the head file. Now, this one people will often tell you is really important in Git, and they're not wrong. They'll often say like, oh, head is what you're pointing at. It's what you're looking at. And, well, they're exactly right. This head file contains that pointer. You're either pointing to the tip of a current branch, like, oh, feature branch, I'm looking at that, or you're pointing to a specific commit. Here's an example contents if I'm pointing to the tip of a branch. It's this weird refs head main, refs head develop. We're going to look at refs later, okay? Remember, that's my little promise to you, that we're going to look at refs later in this cave system. But it might say refs main, refs develop. That just means I'm pointing to the tip of that branch. Or if I check out a very specific commit in the past, in the history of this repository, I go into a detached head state, which sounds terrifying, but it means absolutely nothing. Basically means you're not looking at the tip of a branch commit, and in which case the head file might contain an actual commit hash, pointing to a very, very specific commit in the history. Nice. Things are starting to make sense, hopefully. Interestingly as well, head, the file, can also be used as a reference in Git commands. So you can use head to say where I am now. The commit, the thing that I'm pointing at right at this moment is head. But more interestingly, you can use little annotations behind head to sort of say some commits in the past from where I am now. So if I use a little caret thing after head on that second line, oh goodness gracious me, little caret thing after head, that means head where I am now, but -1. So one commit, the commit before where I am now. That's kind of cool. And what about this tilde thing? You can do tilde and X, some number, to say that many commits before where I am now. Nice. Useful. Probably. Next, the orig head, or original head. This file's really easy. Stay with me. This contains the previous state of head, or what head sort of used to be. And it's automatically set by commands that have possibly dangerous behavior. So that if something goes absolutely wrong, you can hopefully slightly more easily revert it. Let me give you an example to highlight what I'm on about. Let's imagine that I'm pointing at this commit, BAT. My head is pointing at BAT. If I use git reset hard for some reason to just sort of like go back to a previous commit in the past, it doesn't matter what this commit is, git reset is one of those possibly dangerous behavior commands. So in that moment that git reset is run, orig_head is set to my old commit. And if we cat it out orig head now, you'll see it says BAT. Ooh, nice, okay. And we can use orig head like we did with head as a reference in commands. If we wanted to immediately check out back to that commit, we can use git checkout orig head, and booyah booyah, we're back at BAE. Booyah booyah. Next, ladies and gentlemen, is the config file. And this is the first file that I'll say to you that you can manually edit yourself if you choose to. This contains the settings and configuration for your Git repository. It's the toggles, it's the tweak, it's the little settings that you've changed for your repository to be unique from Fred's repository over there. The file might look like this. It's a bunch of key value pairs, git hooks, blah, 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 right, under a bunch of headings, okay? You can edit that file yourself, like I said, or you can use the git config command to set them through the command line. You have to pass in a level. We'll come back to level in just a second. A level, and then the key that you want to set, and the value that you want to set it to. It couldn't be easier, but what's that level thing? What's that local thing? Let me explain. Interestingly enough, I'm saying interestingly enough a lot, I'm sorry about that. Quite interesting, Git has 3 levels of configuration across the system, across the machine. It reads from the topmost level configuration down to the local repository level configuration, overwriting any conflicting settings as they come. Let me explain a bit better. There is a system-wide Git configuration file, which is found in etc git config. And this is for every user on the machine. And this was more important back when we sort of like shared machines. You know, you're sort of like signed onto a remote machine somewhere, but nowadays it's pretty useless. It's a system-wide configuration that can be accessed with --system in the commands. So Git reads in the system level configuration down to the user level configuration, which can be accessed with --global and is a file located in the home directory of the user under .git config. That's a configuration for every repository of that specific user. Every repository of a specific user. So it reads system, it reads user, overwriting any conflicting settings as it goes, and finally it reads our local project-specific repository configuration file, which is in the .git folder, where we are now, in the config file, right? And meaning that this final level, this configuration just for this repository has the highest priority. You know, if you set a setting that conflicts with the ones above it, the one at this bottom most local level will take priority. Git reads system, user, repo, and then it spits out your current configuration for that repository. You can list your current configuration with --list, but very interestingly, if you add --show origin, for each line of outputted configuration that comes out of Git, it tells you which level it came from in the Git configuration. That's pretty cool. Let's keep moving. We're running out of time. The description file next. This one's garbage. This is a relic of times gone by, and you'll never need to edit this, but you can if you wish to. This is when people used Git Web or Git Instant Web. They'd spin up this like sort of Git server, and this file, the description file, would be populated somewhere on that server saying, oh, this is what my repository is. Let's keep moving. You don't ever need that one. The index file is vitally important. We're going to spend a couple of minutes here investigating this. This is a binary file, meaning that if we pop it open, we can't just read it. It's like this sort of nonsense garbage that we'll get. It contains a list of paths, permissions, and SHA-1 blob objects. Oh, memory tingles triggering. In this file, but what is it actually doing? It's tracking changes to your files. You can just think of it as tracking changes to your files. There is a really wonderful article that's included in the link tree, which you'll see throughout these slides, that explains the format and the layout of this index file, because we don't have time. It would take hours to sort of explain each bit, but it's really fascinating if you're interested in learning more. But we can query this index file a little bit using the plumbing command ls-files. This plumbing command just simply says, it tells you information about the files that the index file knows about. Let's understand how that works. If I use git ls files in a repository, it says, oh yeah, I'm indexed, I know about file 1 and file 2. Cool. If I then create a third file, please note, I have not added it. I've not added it yet. If I use ls files again, index goes, get file 1 and file 2. They're there, I got them, that's good. If I finally then git add that file, in that moment the index file is updated and changed, and if I use ls files now, index knows about all 3 files. Okay, cool, so git add is sort of a mechanism to affect the index file. Let's look deeper. I have a visual representation for you, because visual representations are awesome. I'd like to show you, explain these 3 columns before we go in. First, on the left, we have our working directory. This is our file and folder where we're doing our work on our code or files or whatever it is. In our case, we just have one file, 1.txt, to keep it simple. In the middle is the really important bit. This is a visual representation of the index file. It is not accurate, it's a visual representation. And inside that, you have this little yellow box that is sort of the information that's stored in the index file. So this little box is sort of the information that's stored in that file. And finally, we have our objects directory. Now, I don't want you to worry about this bit because we will see lots of objects later. But what I would like to point out and remind you about is commits in red. Commits in red point to trees in blue. And trees point to other trees or blobs in green, okay? So this is a visual layout, a visual understanding of our repository at this moment. Let's make some changes. If I edit file 1, just edit it, I haven't added it yet, I haven't done anything. If I use git status, in this moment Git quickly hashes the contents of 1.txt, and it's got that hash, and it goes to the index file and compares it with the information that it has in the staging area column of the index file, if you like. And then Git goes, oh no, they're different, gross, ugh. And that's how Git is able to say, oh, you've modified a thing, but you've not added it, dum-dum. Nice. Once we use git add on that file, that is the moment that the index file is updated and something else interesting happens that we'll talk about in a second. But when we use git add, the index file is updated. When we use git status, it goes, working directory version versus staging is same. Nice. Then it goes staging version versus the one that I know about that's sort of like committed, locked into the Git history. Well, they're different. And that's how Git's able to say, yeah, you've modified a thing and you've added it, but you have yet to commit it. This is how Git's able to understand where those changes are in our sort of layout. The one other thing that's really interesting here is the moment that we use git add, in that moment, Git creates the blob object for those changes and sticks it in our objects directory, which we'll see later. Sticks it in the objects directory, but it's dangling. It's not connected to anything. I don't know if you can see that. It's not connected to anything. It's just dangling. It's just there. Interesting. When we use git commit, finally, the index again is updated and all 3 columns are the same. So Git is able to say, oh yeah, clean working tree, nothing to commit, good job. And in that moment, our commit object was created, our tree object was created, and it was all connected back to that poor little dangling blob. Nice. So the index file. Really interesting, really important. The final file before we move on to the folders, and I hope you're all with me. We've got to keep moving fast. We're running out of food. The packed refs file, this is boring. This contains a list of dormant refs. It's similar to information that we'll see later in the refs folder, which we will see later. The file looks something like this, and again, it's a commit reference pointing to a ref thing that we have yet to learn about. But why is this file here if it's so boring? Well, this is something interesting. You'll see a bunch of these efficiency files around Git. These files that Git sort of just throws in all over the place to make it better at doing its Git thing. It helps it speed it up. It helps it index its thing faster. It helps it move quicker, right? You'll see a bunch of these efficiency files all over the place. We'll see some more in just a second. So packed refs. Okay, everyone doing all right? Anyone need an Apple energy bar? We haven't got any left. I'm sorry. You have to go without. Take a couple of stretches. Let's do some of this. I don't know what the hell this is. This is weird. Anyway, we've done the files, and I'm sorry to say that we've not found any clue of an exit. Please don't panic yet, because we have the folders, and I imagine the folders must have something for us. They are vast, and they are deep, and they are plentiful. Please keep your eyes open, and let's keep moving. The info folder. If you hadn't already guessed it, the info folder contains additional information about the repository. Hooray! It's very uninteresting, except for, people always say, the exclude file. The exclude file is like a git ignore file that is not stored in, it's not versioned in the version control system. It's not in the version control system because it's in the .git folder. So it's like a git ignore file that you can have just for yourself, just for you. Ooh, it's my little git ignore file. Yum. Exclude. There's another list of refs. Refs we will come to again later. There's grafts, attributes, blah, 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 blah. It would take me ages to go through all the different cavern tunnel systems here in this little folder, so please check out the link tree if you want a real comprehensive list of all of the little info files that could exist. Let's keep moving. The refs folder. Everyone's like, oh, thank God, we get to find out what refs are. This folder is very important. This is a grand archive. This is a library and contains a master copy of all of the references in the repository. But Ben, what's a reference? References are everywhere, as you've seen. And references are essentially human-readable pointers, human-readable aliases to commit hashes. So instead of saying 682F19B there, I could say feature branch. A nice stringy human-readable thing that points to actually some Git object somewhere down the tree, so I don't need to use those horrible hexadecimal characters. Instead of saying 4FB92, wasn't even close. Oh, it was close. Hey, you got it, nice. I could say, yes, origin main, right? And you get the picture. Instead of saying blah, 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 I could say version 2. So they are human-readable words, stringy bits that actually point to commit objects. Let's look at the folder structure in this refs folder. The heads folder is for our local branches, the things that are on our machines. They contain tip of the tree commits for branches, so the commit that's at the top of the branch. Right? The remotes is the same, but for the remote tracking branches. And remember, we can have multiple remotes in our Git repository. So origin is sort of the default nickname for the server. We could have other things. Origin, my other server, my secret stash repository, I don't know, whatever. And you'd have those folders in there. And of course, we have tags, which point to directly Git commit objects. So it's like, that's version 1 right there. That's version 2. Hopefully it makes sense. Refs. Okay, everybody, we're getting there. Hold on a second. What's that? What's that shiny thing on the ground there? Well, it looks like a... Imagination again, please, people, play along. Here we go. It looks like a weird half-disc thing, and it says cat on it. Weird. Okay. I don't know what this is, but we'll keep hold of it, and we'll keep moving. Come on, keep going, everybody. All right, the hooks folder. The hooks folder is dope. It contains a collection of programs, a collection of scripts that automatically trigger at different moments in the Git lifecycle. I'll explain what I mean in just a second, but side note, by default, all of these programs are disabled. If you would like to enable them, simply remove the .sample suffix from it and they will become active. I don't know what it is, active. Anyway, back to what I'm on about the Git lifecycle. Let's take an example. If I use git checkout and check out a branch, the moment I've done the checkout, behind the scenes, Git goes, oh damn, he's checked out, and he goes over to the hooks folder and he goes, Hooks, is anybody called post-checkout? Post-checkout, where are you? And post-checkout's like, oh damn, that's me. And post-checkout comes, and he's like, run, post-checkout. And post-checkout's like, whoa, I don't know, whatever. It's a script, it's a program, it could do whatever it wants. It's bespoke, right? So post-checkout does its thing, right? And then maybe I edit the file, maybe I git add, maybe I git commit, and again in that moment Git goes, what? Hooks folder, have we got pre-commit? Pre-commit's like, oh that's me, oh god, okay. And then, I'm not going to do that again, I'm sorry. And then pre-commit runs, and we've got hooks, we've got opportunities to hook into the Git process, to the Git sort of, the Git world, and do bespoke custom things. The scripts, we can write whatever we want them to do, right? And there are loads of different hooks, and actually they are not all present. Let me repeat that. All the hooks are not all present by default in the .git hooks folder. If you would like a comprehensive list of all of the hookable moments, then please head to the Linktree and look for this link. There's a bunch of different things you can jump into. But hooks are just programs, and they are language agnostic. So you could write them in Shell or Bash or Python. So let's do an example. Let's write together a pre-commit Git hook. Okay, I'm not going to actually use code, because I don't know any code. But we're going to just use a little bit of pseudocode, and we're going to write the pre-commit hook. When does the pre-commit hook trigger? The moment that the user hits enter on git commit, but before any of the actual commit process happens, that's when pre-commit triggers, right? Hooks goes, oh, pre-commit, it's your turn. So let's put some stuff in our script. Maybe I want to run a lint check as part of the pre-commit. And if the lint check succeeds, I'll say, okay, carry on. Please, feel free, continue. And if it fails, I want the commit process to be aborted. I want it to stop. So I might exit with status code 1. And in the Unix world, 1 means wrong, error, gross, right? Bad, right? So that Git will receive this exit status code 1 and go, oh, something bad has happened. I need to stop the commit process. And the commit process is aborted. We have affected the Git lifecycle with a custom script. That's dope. Maybe as well, I'll run my unit test suite, and if it succeeds, great, we carry on. And if not, exit status code 1, commit aborted. And finally, if everything went well and all is good and the commit, we want it to continue, exit with status code 0. And again, that means, yes, true, correct. Other positive things that I could say, right? And Git will receive this exit code status 0, and the commit process will be allowed to continue. And in this case, it will pass off to the next Git hook, which is prepare commit message. Cool, we've made a Git hook. We've affected our Git lifecycle, our Git process to make it custom. Cool. The logs folder. This one's relatively simple. Again, this is an archive, okay? This is for the recorded logs of Git actions. When you do an action in Git, it's logged, which is dope. And if ever you make a mistake in Git, you'll be very, very thankful that these logs exist. Let's take a look at one of the files here. This is the log for the local branch main, and let's just break down some of these columns to understand what they are. On the left, we have the from commit hash. So before the action was taken, whatever the action is, that was the hash we were pointing at. Then we have next to it the to hash. Once the action was taken, what is the commit object that we are now finally on, right? We have who did it, when they did it, and we have, of course, the action. It was a clone, it was a commit, it was a fast forward, whatever, right? Whatever the action was. Interestingly enough, the command git reflog, which if ever you do make a mistake in Git, I point you to git reflog as your first haven of safety. This command just uses the files and information inside of the logs folder to populate its output. Cool. Okay, whoa. Thanks, guy. This place is weird. What are all these markings? Look at, these are commit hashes, but they look super ancient. Oh, creepy. This place gives me the heebie-jeebies, everybody. Keep close. Stay together. We've got to keep moving. And does anybody get the feeling that we're being followed? Somebody does. Let's go. We are now in the all-important objects folder, and it's where we will hopefully find our escape route. The objects folder is where the Git magic all happens. It's where your changes are stored. If ever you check out another branch, where do my changes go? Well, they've always been here, safely nestled away in the object store. In this folder, Git stores your commit objects, your tree objects, and your blob objects, all side by side in a bunch of folders that have 2-character names. We'll come back to that in just a second. If we were to cat out any of these files, it would all be gobbledygook nonsense because this is all compressed stuff that we will also understand in just a second. But back to those 2-character folder names. Why is that? What is that? This is another Git efficiency. So let me tell you. When we have a object, remember all objects have a unique hash, right? When Git's storing these objects, it takes the first 2 characters of that hash, makes that the folder name, and uses the rest of the hash as the file name within that folder. Why? This is so that Git only has a maximum of 256, because hexadecimal, 256 folders that it needs to index through and move through in order to make it more efficient, faster and quicker, as opposed to having like 1,000 different objects folder all in one folder. Another efficiency. Ooh, Git. Yummy. But how do we look inside of these objects? I hear you screaming. There must be a way. Wait a minute. I'm going to go over here. Wait a minute. What's that creeping out of the shadows there? Top dwellers from the up. Oh, it's hideous, gross, get it out of here. But wait, what's that in its hand? Oh, me found it. In the darkness, you can have it. You can have it if you answer a simple question. Get closer. Who created Git? Well, anyone? Who created Git? Linus Torvalds is our answer. Yes, yes, praise be the great one. Here, take it. I don't want it anyway. And he just scuttles off that way, stage left. Whoa, cool. We've got this other half-metal disc thing, and it says file on it. And it looks like it fits together with the other thing we found. They're sort of pulling on each other. Oh my goodness. Sound effects. And it's glowing. What is this happening? It's like a hologram. And it looks just like our map, but more complete. This is amazing, this Git cat file tool. This will help us escape from this hellscape. Let's use it, everybody. Let's use it to interrogate some of these Git objects. So we can use Git cat file, starting off with the -t flag to say, hey Git, what type of object is this thing that we're looking at? Cat file -t, give it an object. It might say, oh, that's a commit object. It might say that's a blob object. It might say that's a tree object. Cool, things are starting to connect. But more importantly, we can use the -p flag to sort of prettify it, to look inside that object and see some plain English in front of us. If we pass it a commit hash, you might get this sort of output. And maybe some of you are going, well, damn, that looks familiar. Yeah, that's a commit message. And that's a committer, a date, a time, an email address. That's a commit. Yeah, it is. And important to know, in Git, all commits have a reference to their parent commit, where they came from, the commit just right before them. They all have a reference, and this is called a DAG, a directed acyclical graph, which means that there can never be any like circular dependencies, and it also means that you can take any commit in the commit history and find your way from parents, 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 all the way back through to the start of time. Yes, the start of time. And as promised, inside the commit object there is a reference to a single tree object. Ooh. If we pass git cat file -p, the tree object, it prints out this, a list of files and folders, a list of blobs and trees, a list of blobs and trees. That's cool, okay, so it's like our folder representation. And if we pass cat file -p, a blob object here, it says the actual contents of the file in plain English. It says hello world, or this is my script, or whatever it says, right? And just to sort of point back out there that the tree hash can contain other trees. So we've set up our project structure within the Git objects. Cool. Okay. We're getting somewhere. But let's just take a step for a second, right? And understand how Git's actually storing. When we make a change, how is Git taking that file and putting it in the objects directory? We've got file 1 here with some code in. When we git add it, Git will quickly hash the contents of the file to give us that unique SHA-1 hash. Cool. So we got that. The second step it'll do, it'll put the contents of the file through Zlib, a compression software, right? To take it and squeeze it down and make it more efficient to store on disk. And finally, Git goes to the objects directory. It creates our folder, like I said before, it creates our folder with the first 2 characters of that hash, and inside that folder it makes a file and sticks in that lovely compressed, juicy content. I don't know why it's juicy. And that's how Git stores objects. That's dope, that's cool to know. Okay, we're running out of everything at this point. We have 2 more folders to look through. Keep your eyes peeled. We have the info folder within the object store, and this contains additional information about the object store in particular. There's this one file that's quite interesting called commit-graph, and this file contains a graph-like structure that Git can understand with some metadata to help Git speed up graph walks. What the heck's a graph walk? Remember I said each commit knows about its parent, knows about its parent, knows about its parent? This process is called a graph walk, and it happens all the time in Git, and it can be very, very expensive if you have a massive repository. So this file is another efficiency thing, hooray, to help Git go quicker. And there's also this packs file, which contains a list of packs in the object store. Ben, what's a pack? Oh, I'm glad you asked. Packs, we need to step into the final folder here in the Cave system called pack. Packs are interesting. Let me first take a step and explain how we're storing the objects at the moment. You know, with the 2 character folder names and the files like that, that's called loose objects. They're sort of just, you know, we throw them into the object store and we shake them around. I don't know, they're in a big barrel here or something, right? They're called loose objects when they're stored like that. Packed objects is the alternative to that, and is something called pack files, which is where Git wins the game of version control systems. That's it. And you'll find these pack files inside the pack directory. What's a pack file? A pack file is a binary file that's used to save space and make Git more efficient, again. And it's essentially a big old file that stores object after object after object after object inside the file in a compressed form. So it's like commit, tree, blob, commit, tree, blah, 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 in one big file. Doesn't sound very efficient. Pack files come in pairs. There's the .pack file, which is the one that I just talked about, compressed literally list of all of the objects and their contents, and then an index file, which is its partner. And in the index file, it has a reference to each of the objects in the pack file with an offset and a size. So Git, if it needs to quickly get to one of these objects in here, goes to the index and say, yo, where is this object in that pack file? And it gets the offset, it needs to jump into byte 381, and it needs to read for 30 bytes or something like that. That's cool, another efficiency. But let's just take another step back, a triple step back from pack files and understand how Git's actually storing loose objects to understand why pack files are so necessary. When we're making a commit in Git, for example, we got this file, right? Here is some lovely text in this file, whatever, it's 32 bytes. We make a commit, we got a blob object, cool. If we come back in the future and edit that file, if we add one teeny tiny line to that file, when we do the commit process, Git makes a brand new blob, different to that one, containing the entire contents of the file again, which is super inefficient because most of this information is there. It's like just duplicated. What a waste. But this is where Git GC and pack files save the day. Git GC is Git's garbage collector, and you never need to run this yourself. It's automatically run on a bunch of different Git moments. And at a really high level, what Git GC does is this. Takes your loose objects and, deletes them. That was me kicking the loose object barrel. Deletes them. It doesn't delete them, but it deletes the objects in the loose objects and gives you back out a pack file. You know, the big pack file with the commit, whatever. Cool, okay. But more importantly, Git GC has the ability to find objects that are similar and then only store the deltas, only store the differences between those objects. People will often start by saying, oh, Git's great because it only stores the changes between commits. That's wrong in loose object terms, but in pack files, that's exactly right. So let's take our example we had before. We've got our 2 blobs, cumulatively taking up about 70 bytes, waste of space, most of it, right? If we run Git GC on that, those loose objects are deleted and a pack file is created. In the pack file, we will have a reference to the original blob, the one with the text in. Here's some text, 32 bytes. And instead of that whole blob again and our little extra bit, we just have our extra bit. We just have our diff. We just have our delta as another opportunity in the pack file, so 10 bytes maybe this time. But importantly, it points back to its original blob, its parent blob, its blob that it is changing or diffing or deltering. That's cool, pack files. So instead of 70 bytes on disk, pack files saves the day and makes it about 40 odd bytes. Cool. Okay, and we can sort of look at the pack files. Not really, we can sort of look at the indexes of the pack files with git verify pack -v command here. we can pass that a pack file and we get output that looks something like this. This is sort of the index. This is like a nice clean version of the index, right? The first two columns is the hash of the object. You know, what is the hash ID of the object and the type of object it is. At the top it's saying, that's a commit with this hash. That's a tree with that hash. Nice. Makes sense. Next, these columns are really, really important. The first one on the left, it's the size of the object. The one in the middle, it's the size of the object in the pack file after a little bit more compression. And the last one is the offset, where that object is in the pack file. So that Git can go for this first one, it can go, I need to jump to 2057 bytes and I need to read for 195 bytes and I have that object. That's cool. But the real power comes in that last column. And I want to draw your eyes just to these bottom two lines here. Going back to our example, our two files. This DDA1 blob, that's our first file. This is here's some lovely text, it's 32 bytes, whatever. And the line beneath it, our extra blob, 10 bytes. Instead of this being a 42-byte mammoth thing, it's 10 bytes. It's just the delta. It's just the difference. And right at the end there, it points back to the base SHA-1 hash, the one above it. It's saying this is the thing that I'm extending or changing or deltaing. Ooh, pack files. Okay, everybody, I have terrible news. This is where we live now. And we won't be living for much longer with the food supply that we have left. Wait a minute. What is this big, bolder, other hash thing that's on the wall here? Why is it bolder and different from the others? Ugh. Well, we can maybe use our cat file tool to see if it can tell us something a bit more. So let me take our cat file tool and let me type into the thing, even though there's no keyboard on that thing. And we've got the hologram again. And whoa! It looks like a root. It looks like an escape route, everybody. Follow me, let's go! Caves, 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 caves. Whoa! It's free. Oh no! Spoilers! We did it! Amazing! Freedom! Freedom! Damn, we just showed that creature the way out of the cave system. I don't think that's going to be happen back to this world in the end. Come on, everybody, we made it out. Let's get back to Basecamp Git. Oh, well, I think that went well. Frankly, the fact we didn't need to use those health and safety waivers is really, really lucky for you guys. But I hope you enjoyed it. Thank you all so much for the adventure. If you want any of the links, the articles, the videos that helped me create this presentation, the link tree is there with a QR code for scannable reasons. I've been Ben Cadell, if you've enjoyed this talk. If not, just make up a random name and tell people it was all right. And thank you so much. I hope you enjoyed your adventure into the .git folder. Thank you.